Hi again everyone. In this simple video we're going to look at the comparison theorem or the comparison test from the subject of infinite series. Okay, so let's look at the actual comparison test first. Alright, here it is here. Now the basic idea with the comparison test is that you're comparing one series with another. Okay, so consider the given infinite series sigma a sub n, where each a sub n is non-negative. Right, there's two parts to the comparison theorem. If we can construct a convergent series, sigma bn, such that, I guess, all the an's are less than or equal to the bn's for each n, then the original series converges. Okay, if we can construct a convergent series, sigma bn, such that an is less than or equal to bn for all n, then the original series converges. And conversely, if we can construct a divergent series, sigma bn, such that the bn's are less than or equal to the an's for each n, then the original series also diverges. Now, let's have a look at the following example to see the application of the comparison theorem. And basically, the idea involves inequalities. Okay, now here I've said if we can construct a convergent series, if we can construct a divergent series. Basically, really all we need to know is these two things exist. All right, but when you apply the comparison theorem, this is actually what you're doing. You're constructing a certain series. Okay, so here's our given series, and we're asked to discuss whether the series converges or diverges. Now for this we use some inequalities. Okay, so the inner monologue is basically about applying inequalities to get one of these. Okay, so let's look at one on n squared plus 3. Now, for each n, this is less than or equal to 1 on n squared for each integer n. Now, where did that come from? Well, it comes from the simple fact that n squared is less than or equal to n squared plus 3. So you just divide, and you have this. Okay, so we've come up with an inequality like this one here. Okay, so now we need to go, okay, well, if that's my b sub n, right, does the series associated with 1 on n squared converge? So let b sub n be 1 on n squared, and note that the sum of 1 on n squared, well, that is a p series, a power series. The power is equal to 2, and it's a convergent power series because the power is strictly greater than 1. So we realise that our constructed series is a convergent p series. Okay, thus our new series converges. So you can think of this as a bigger series. And so by the first part of the comparison theorem, we've constructed this convergent series with this inequality, and so the original series must converge. So we go back here and go, okay, this original series must converge by the comparison theorem or the comparison test. So our AN, which is sum of 1 on n squared plus 3, also converges. Now, in the original statement of the theorem, I've said it's the simple version. Well, you don't need these inequalities for all n. All you need are these inequalities for little n large enough. Okay, and the same one with here. Alright, now in the next video we'll have a look at how we can apply this part of the comparison theorem.